possible force, and that is the weight of the object. Now that's a tricky one to draw because there's weight here, there's weight there, here, everywhere on this thing though. It's not like all the weight is in one spot. It's spread out all throughout the object. So in that case, we're going to put a dot near the center of it. The weight points downward. So I'm going to label that one as W. So the diagram is nice. It shows you where the forces are occurring. It's a good idea to draw diagrams like this, but it's very difficult to draw it with pencil or a pen because you're just putting lines on top of pre-existing lines, and so it makes it difficult to know, like, what is the actual length of this arrow? Is this arrow the length of the whole thing? Because this is the physical string. So it makes it difficult to draw those on. So for that reason, I'm going to ask you to draw in the second method instead of the first method. So what the second method says is, rather than even drawing the object, let's just draw the forces acting on the center of mass. And all we need to represent the center of mass is a dot. So that's the sled right there. That dot represents the sled. And I'm going to identify all the forces acting on it, and I'm going to make those forces point outward away from the dot in the direction that the force is pointing. So let me go in sort of reverse order now. We said that there was weight. The weight acted in the downward direction. The surface of the ground pushed against the bottom of the sled. That is called the normal force. There was a little small frictional force. This is on the snow, remember, so not a very strong frictional force. And then the tension is pointed at an angle like that. Those are the four forces. I'm sure you can appreciate that that is a much cleaner diagram. It's easier to see all the forces. I can think about the physical picture, and I'm not saying you shouldn't draw this picture. It may be helpful to draw this picture, and I would not discourage anybody from doing that. But I just don't like to draw the free body diagram directly on the object because it takes it and makes it very cluttered. It makes it very difficult to see. What I would rather see is a nice clean diagram, clearly labeled, forces pointing in the correct direction, all radiating away from the center. If there was another force in the upper direction, I would just tack it on to the end of it. I would just add it to this one because that's how forces work. They add. So when two forces point in the same direction, we add their forces together and we draw their two arrows end to end like this. So let's take a look at some other situations, other possible ways. Well, similar forces, but with a different circumstance. Let's take a look at the forces that are acting on an airplane if the airplane is flying through the air. So nothing in contact with the ground. So a plane flying at a level altitude, and it doesn't say traveling at a constant speed, but we're going to assume that this plane was traveling at a constant speed, and there's the plane. No artistic ability required. Obviously, like all objects, planes have mass, so therefore planes have weight. Now, is this weight arrow the same as the previous weight arrow? No, it's definitely not. This was a little small sled, so this might have only been 20, 30, maybe 40 newtons. And we're talking about an airplane, which is going to be in the ballpark of millions of newtons. But what is important about the arrows is not how this arrow compares to some other drawing, how the arrow compares to this drawing. So I want the plane to fly at a level altitude. I don't want it to go up, I don't want it to go down. So I'm going to draw it with the upward force equal in length. I purposely am trying to draw these two arrows to be equal in length. And the name of the upward force that acts on airplanes is not the normal force, but the lift force. The force that propels airplanes forward is called the thrust force. The force that resists, the resistive force that airplanes feel when they are in the air, is called the drag force. Okay? Now, the way I've drawn it is I'm saying that the thrust is more than the lift, or that the thrust is more than the weight. And I know it's more than the weight because I drew it longer than I drew the weight arrow. Right? So this is the thing that you're going to be asked to do with free body diagrams. It's not just identify the names of the force. It's not just point them in the right direction. It also includes making the lengths correct. And that's going to get easier as we start talking about the first and second law. In the next videos, we'll talk about how do you know which arrows are longer, which ones are shorter. You have to know something about the motion of the object. So let's take a look at the, we actually drew, I think, almost every force that was acting on this. So if we put a box back on that inclined plane, that's just a ramp, remember? So that's the situation that we're talking about. I just wanted to draw this one because I don't know if that's clear what it means by an inclined plane. So I'm going to draw over here to the right the free body diagram for this thing. I would say it's a no-brainer. First one I'm going to draw is going to be the weight of the object. Okay, now there is a normal force, but in this case the normal force doesn't go against the weight, it's tilted over because the surface is not flat, or horizontal I should say. Because it's tilted at an angle, that means that the normal force, I'm trying to draw this so that it's perpendicular to this surface. The normal force is always perpendicular to the surface. There is no tension. There's no thrust. There's no drag force because this box is at rest. There is only one other force that is acting on this object, and that is the force that is preventing it from sliding down the inclined plane. The weight of the object is trying to make it slide down the inclined plane, and that is the frictional force. Just to remind you, frictional force is always parallel to the surface and always opposes the motion or the intended motion, which in this case the intended motion is down and to the left. And that's it. Those are the only forces acting on it. And that's a difficult thing to know. Like, when do you know that you've identified all the forces? It's a challenging thing to do. So what I would suggest that you want to do is, I've named the 8 most common forces. I would just run through those forces and just think, is it there? Is there tension here? No, because there's no rope here. Is there a buoyant force? No, there's not really a significant buoyant force because this isn't floating in water, or it's not in anything that would produce a buoyant force. So you really have to sit there and just go through and think about what are the possible forces and just check them off one at a time until you've gotten down to whatever remains. That must be the forces that are acting on it. Let's take a look at one similar example to this, and we're going to finish with these last 2 examples. Let's say that the box was being pushed up the inclined plane. So in that instance, we would still have weight. We would still have a normal force. But now we would have another force, this time the force pointing up. And when you have a person that is exerting a force, we generally refer to that as F of A. So this is, the applied force. That just means that some person is pushing on it. It's technically a normal force, but if we label that as the normal force, well, then that's confusing with the normal force that comes from the surface. So anytime a person or an animal or some object is pushing against it, we oftentimes just refer to that as F of A, the applied force, some external force being applied to it. And in this case, because the object is actually being pushed up the inclined plane, that means that the frictional force is going to point in the opposite direction, down the inclined plane. So that's quite a complex drawing. When you have the box being pushed up the inclined plane. Okay, that's going to leave us with one last example that we'll take a look at, and that is the forces acting on a skateboarder who is coasting to a stop. So not putting their foot down, not pushing against the surface. Right, so there's the skateboarder. We're going to assume in this particular instance that they are moving to the right. These little lines that I'm drawing right there, those are from the drag force. That's the air going around the person, and you can feel it. You can feel that air as it moves past you. So obviously, you know, a skateboard is just to make sure this is really important, we're talking about the skateboarder. Okay, we're not talking about the skateboard. The skateboarder is the person. So we're very concerned about the person who's standing on the skateboard. So first of all, there is weight, that goes without saying. There's an upward force on the person that comes actually from the skateboard itself. I'm going to draw that one the same length as the weight arrow. I know that those two are balanced because there's nothing happening in the up or down direction. In the vertical direction, nothing is happening. So I know those forces are balanced. But it says that the skateboarder is coasting to a stop. Now, if they don't put their foot down, there's no thrust, and there's certainly no engine on this particular skateboard. So there is nothing producing a thrust force, but there is a resistive force. And there's a whole bunch of ways that we could label that. I could call it F of F, or I could call it F of R. It's really a combination of two forces. There is friction acting on the person. There's friction in the wheels of the skateboard, and then of course there's friction between the surface of this person and the surface of the skateboard. But there's also a drag force. I mean, clearly air is being pushed around you. So why do you slow to a stop? Well, it's a combination of all those things. It's the frictional forces inside the skateboard, and then also the drag force that is going against you. And both of those things are going to bring you to a stop. You could call it F of F, or you could call it F of R to represent all of the resistive forces. I would probably not call it just F of D, though. And the reason I wouldn't call it F of D is because that's not the only kind of resistive force. There's also frictional force in the wheels that is acting on the person, bringing that person to a stop. And so this is the best diagram. What would be happening in a diagram that looks like this? This is something where either the object is accelerating in this direction, it's picking up speed this way, or the object is traveling to the right, but it's slowing down. And so that should give you the basic idea about how the free body diagrams work. Just give you the basic outline. It takes a little bit of practice. It's not easy identifying all the forces, and oftentimes you may get to where you feel like you've identified everything, but there's still one force missing. So again, I would suggest that you go through each of the 8 forces, think about whether it's there or not, check them off, and at the end, once you've gone through those 8 forces, you should have identified all the forces that were acting on the object.